Hey guys, this is a recitation for homework 6 of practical data science. The assignment was released last Saturday, so the due date is going to be Saturday, December the 3rd. This homework also, as usual, contains three notebooks, one on MapReduce, one on deep learning, and the other on probabilistic modeling using PYMC. The grading is going to be slightly different from the other notebooks because you also have a project which is going on. So all notebooks are weighted equally, 33 points each, except deep learning, which also has a contest at the end of it. So you can score up to 38 points on that one, 5 points extra. The 388 students are required to do just one out of three notebooks, and 688 have to do two out of three to score full points. Over and above this, you can get extra credit by attempting one other notebook. Extra credit is going to be half the points allocated for the notebook, and it will be applied even if you have scored like full on the previous homework. So you can go above 100 on notebooks, on homeworks. And the auto grader for this notebook would be out in a couple of days. So the first one, let's jump into MapReduce. So this notebook does not require the use of any new libraries. We'll just be using the MapReduce class that is implemented in the notebook itself. The notebook already contains an example as to how to use the framework. We'll just go over this now. So the example is for word count, the one which is covered in class itself. So the problem is, given a corpus of documents which contain words, you want to find the number of times each word, which is not a stop word, occurs in the entire corpus. So you want to parallelize this by processing all the documents simultaneously as much as possible, and then you want to aggregate the counts. So if you've attended the class, you might know that the way you would implement this using MapReduce is, in the map phase, you would emit a word. So you process the line of each file one by one, and for each word, you just check if it is a stop word or not. If it is not a stop word, then you would emit a pair saying, I've seen this word exactly once. And in the reduce phase, you get the list of counts for every word. It's going to be grouped under the hood. And you're simply going to add all these counts and emit word, comma, the total number of times you've seen the word across all documents. So the notebook already contains the framework, like I said, and also this particular word count examples mapper and reducer functions. I've just pasted this into a Python file which I'm importing. So this is the framework, the class name. This is going to be the mapper which converts files into word comma count equal to 1, and this is just going to aggregate the counts. So let's look at how to use this framework. So I'm just going to create an instance of this MapReduce job by passing in the mapper function, the reducer function, and also telling how many worker threads I want to create. So the number of workers can be anywhere from 1 to how many ever you want. But if you set this to be none, it will directly take the number of CPUs that is available in your system. And that's the till that point you can see improvement in performance in terms of time. So once this class is instantiated, you want to pass the input to it. So I'm reading the input files, which is just a list of RST files that I've stored in my local system, which is also available to you. So to run this MapReduce job, I simply invoke the call function, which can be invoked by directly calling the object itself as a function. So for instance, word count job of, and it has two parameters. One is the input files itself, which is going to be a list of file names, and the second is the chunk size. So how many elements in this list should one mapper process? So if I said chunk size equal to k, it means each mapper is going to process k files. And a particular worker thread can, so worker and mapper are different, as you might be knowing. A particular worker thread can run multiple mappers in a sequential manner. So the parallelism really comes from the number of worker threads you have, which is like more than one. So if I run this, so I see that there are two worker threads, and they are processing 4 files. So one worker thread has like processed like 2 files. And here you have the output. So here 1 through 6 are the words that the files contain. They are really small, and this is the number of occurrences of each of them. Are there any questions on how to use this? So one other thing I probably didn't mention is you also have something called as the worker context that you can pass to your init function. So what this does is if you want to have some global data which you want to be shared across all mappers, then you can pass it here. For instance, if you want to have a dictionary which is going to be shared by all mappers, that can be done here as well. And this will be useful in the k-means problem that is there in this notebook. Any other questions?
This particular notebook uses a library called unsupervised.
Yes, so this is going to be the homework that you've already done in a notebook that you've already done in homework 5.
Yeah, I think that's not mentioned anymore.
I see. Okay. Yeah, I'll see that. Okay. So that is for the k-means clustering part. Yeah. Any other questions? Okay. So the next notebook is on deep learning, which will use 2 new libraries. One Pillows for image processing, because you'll be working with pets dataset, and also one on Keras, which is the deep learning front end you'll be using. The backend can be Tiano, which we are not offering much support for, and also TensorFlow, which is recommended. All of these have to be installed separately. They are not available with Conda. So I'm not going over the installation. If you have questions, please let us know on Piazza. So how to use Pillows? Pillows is the Python imaging library. The most important class here is the image class. So you can create an instance of this class in a variety of ways. You can create an image from scratch or by opening an image file like JPG. And here I've mentioned an example as to how to open a file. So it's just simply image.open of the absolute or relative path to the image file. So this returns an image object, not surprisingly. Okay, and this displays the image. So now that you have an object for image, you can view some properties of it and also display the image itself. So one is like IM format. Here in this case, this is going to be a JPEG image. Not surprisingly, it was a .jpg file. This can also be PNG or whatever. Im.size describes the number of pixels you have, width and height. Im.mode is going to display the color mode. It could be RGB or CMYK, grayscale, whatever. And you can simply show this by using im.show, which is actually going to annoyingly open a new window. So we'll just be using, plot.imshow, which is available with the pyplot matplot library. So yes, so this is the image. So here an important thing to notice is, so this is going to be the x-axis, which extends rightwards, and your y-axis increases like downwards. You had 225 cross 300. So once you have viewed the properties of the image, you might want to do some basic processing. So one is you want to say convert all the image files you have into the same color mode. So for instance here, as an example, I'm converting this into grayscale mode, which is LA, im.convert of LA. If you want to convert it into RGB, then you simply pass RGB instead of LA. And if I show the image, here you have the black and white form of the image. So this is how you would convert formats. The second is how do you crop this image, because images might be of different sizes, which means you get feature vectors of different length, which is not desirable. So you want to bring them down to the same size, same number of pixels along width and height. So by cropping, you simply do im.crop, and you specify the starting point of x, the starting point of y, the ending of x and ending of y. So for instance, this is going to select the pixels Along x-axis, it's going to select 50 to 200. You can see here. So this is around 50 to 200. And along y-axis, it's going to select 0 to 250. So you have this cat picture. Um, so yes, so this is how you're going to bring down every image to a square sized image. Square size does not mean that you still have same number of pixels along width for every image. So you're also going to rescale images irrespective of their original size. How do you do this? You simply use the im.resize function and pass in the number of pixels along width and along height you want as a tuple. And the second parameter here is the filter parameter, which is going to describe how exactly the final pixels are like downsampled or what. So the default parameter here is the image.nearest, which does sampling by using nearest neighbors. But the Python official documentation itself recommends image.anti-alias, which is what you will be using for this notebook. And in general, this is preferable unless you're really concerned about the speed at which images are being scaled up or down. So this concludes the part of the useful functions from Pillow you will be needing. Next is Keras. So it's a Python library for developing and evaluating deep learning models. It's simply a wrapper around any of the Theano or TensorFlow numerical computation packages that you have underneath. So these are the imports that are useful for this recitation. And the example that I'll be going over here is based on this particular link, which you can feel free to go through. There are also a lot of useful links from this page if you want to dig deeper into these libraries. So we'll work with randomly generated data containing 8 feature values, each having a binary output, which is 0 or 1. So this is a binary classification problem with all real valued inputs. So in this cell, I simply just create the inputs. A side note here is it's always a good idea to specify to pass in a known seed value so that you can reproduce any experiments you do. So here this is going to be an n cross d, n cross 8 matrix of points, and y value is simply an array of values between 0 and 1. So the first step is to create the deep learning model itself. And as many of you might be knowing, a model is simply a sequence of layers. So we are going to initialize the model by saying, okay, this model is going to be sequential. I'm going to be building it one layer at a time. And we specify the input layer first, the first hidden layer, and so on till the output layer. A couple of points. The first layer should take in the correct input dimension, which is same as the dimensionality of the input itself. So here it should be 8. And the last layer should have the same number of neurons as the output dimension. So here it's a binary class problem. You expect a scalar output, so it's going to have just one neuron. So how to decide the number or type of layers? This is a hard question, and usually it's just by trial and error. The general rule of thumb is to have as big a neural network as possible, constrained by the data that you have available to you. So in this homework, we'll just be using a pre-trained network, VGG, which there are links to in the notebook itself. But here we'll be going over how to create and train a network from scratch for the example that we have. So we already initialized this is going to be a sequential model. Now I add the first layer. These are all going to be dense layers because I'm going to be creating a fully connected network structure. So the first one indicates what's the number of neurons in this layer. The second optional parameter is what is the input dimensionality. So this has to be mentioned explicitly. That's an important point. And how am I going to initialize weights for this layer? I just uniformly sample them. You can also do normal sampling. And the activation unit type. So that's going to be ReLU here. It's known to work well in practice for hidden layers. So that's what we'll use. The second layer, it has 8 neurons again, similar initialization of weights and activation. And finally, I had the last layer, yeah, which is 1 neuron, which is equal to the output dimension, and weights initialized as usual. And we'll have a sigmoid type of units because we want like probability score as output, so it's interpretable for this particular example. So in the notebook, you won't be creating these dense layers. You will be using convolutional or max pooling or zero padding layers, which if you go through the VGG documentation, you'll know. And these are known to work well with images. But the basic procedure of how you add layers remains the same. You would just be using, say, convolutional of whatever inputs you pass in there. Um, So once you have created the model, you have to compile it, which means you specify what is the loss function which you're going to use to learn the weight parameters. And also what is the optimizer you're going to use to search through this weight space. And what are the metrics you're interested in monitoring through the training process. So here I just have accuracy, and these are some values that I chose to pass in.
What does
Um,
optimizer do?
it's going to determine how you search through the weight space. Like say gradient descent if you want to do. That's going to be one type of optimization. Um, okay, so yeah, and so how to train and evaluate? I'm just going to fit this model that I've created to the x and y values that I already have, and say I'm going to run this for 150 epochs, and I'm going to process like 10 data points at a time. This is going to take a while. You can see the output here per epoch, and the accuracy is sort of increasing, and it goes up to zero point 0.8, which is wonderful because we created the x values just randomly, so it's able to learn something from that, which is nice. Um, and you can evaluate this model by passing in again x and y parameters, and you can view the scores at the end. You will see 80%. Which is nice. And once the model is created, you can make predictions on it by using model.predict. This is going to give, as we saw, a probability value between 0 and 1, the output of the sigmoid function. And you're going to round this off to infer class labels. And this is the end of the recitation on deep learning itself. Do you have any questions?
I have one question. So you said you recommend TensorFlow, but the homework notebook says recommend Steep.
I see. Okay, whatever the homework notebook says, sorry. Yeah. Okay, cool. So the next one is energy disaggregation. This uses the PMYC library, which is probabilistic modeling. So how do you create a probabilistic model? The basic element is to initialize like random variables of different kinds from different distributions. This is quite simple, as we'll see here. For instance, if I want to create a variable from a uniform distribution, so pm.uniform of t is going to be the name of the variable itself, which can or cannot be same as the variable name that we have here. One is the lower bound of the interval. 0 and 1 are the lower and upper bounds of the interval. So these are like the distribution specific parameters. And this is going to determine the type of distribution itself. For instance, if I want a normally distributed variable, I pass in the name of the variable, the mean, and the inverse variance. That's a key difference from normal SciPy related libraries you have. So this is going to be 1 by sigma squared. You can find the documentation for the parameters for various distributions. So these are individual variables. Sometimes we also want to have vectors of variables, or we might prefer to group them together in some way. So here I want 100-dimensional vector of uniform variables, which I have in X. So I have a container. I initialize a container of 100 uniform variables, each of which is drawn from the 0 to 1 interval. So this is how you do it. Similarly, if you want a vector of normally distributed variables, this is one way how you can go about doing it. So here the distribution of these individual variables need not be the same. So it is the same for this one. So these are IIDs, but here I have a different new one for if x value is less than something, and a different mu otherwise. So that's like perfectly fine. These need not be IID. So once we have these variables defined, we can create a model out of them. So this is simply pm.model of the vector of variables that you have. So this returns the pymc dot model variable. So this just creates the variable saying what distributions, etc. Now we can draw samples from this, which is done by using model.draw from prior. So after making this call, it doesn't really return anything, but the dot value property for every variable, say t or tau or mu1 and mu2, are going to be populated. So you can read off the t value that you have in this sample by using t dot value. So we can also, so this is simply to see how the x value and y values are. I've just created a plot here. So your x is like uniformly distributed, and yeah, so this is based on whatever you have initialized the prior to. And for this sample, you can also evaluate the log likelihood by simply doing model.log p. It's going to look at the sample it currently has and return the log likelihood. So in addition to this, so these the variables have been unknown. You can also create initialize observed variables by passing in the value parameter. So here, so your x initially was, so I create a vector of say random variables x naught and y naught, and as before, I am creating x variable which is a vector of uniformly distributed variables, except I pass in the observed equal to true value, and I pass in what value I have actually observed for these variables. Okay, I hope that's okay. Otherwise, we can take it up later. And similarly, for this y variable that I created, I can again pass in observe.true and the value of y that I've actually created. So this is going to be the ith value. And again, as before, this model, you can create a model from these by using the same function, except here your x and y are going to be observed with the values that you pass to the model, and all other all other variables are unobserved. Now we can create an MCMC object and draw samples from it. So here I'm drawing like 100 samples and saying, okay, the first 100 samples might not really follow the distribution, so I'm going to discard them. That's the burn value. And so here is how you access these samples after, say, initial 100 by using the dot trace function. And here I'm simply plotting the distribution of them, of the tau values in specific. So you can see this here. And how was your tau initialized? So your tau was initialized as gamma of 2 comma 1. So if you go back and look at how a gamma distribution looks like, it's probably something close to this. Okay. The next part is how do you actually index into these arrays of variables that you have created? Say you have a categorical variable z, which is just going to be which is going to take values from 0 to 3, and you have a vector of, say, means for the Gaussian mixture model. You might want to sample a value of z and index into mu. Say you might want to do mu of z, but that's not allowed by PYMC. Instead, what you have to do is pm.index of mu underscore z, which was the name of this variable, and mu comma z. Is that fine? So this is how you, so instead of doing this, which is what you would expect, you have to do this. And this might be necessary in your homework. Any questions at this point? Okay, so let's see how we can put together all this to create a Gaussian mixture model. So this is actually a Bayesian Gaussian mixture model, and it is defined by these parameters. So here, the hyperparameters for this model are theta, sigma squared, alpha, and beta. So so mu and tau are going to be k-dimensional vectors. One of means drawn from this distribution, and the other of these inverse variances. And we are also going to have a Dirichlet distribution with hyperparameter theta. And using this phi, we are going to draw categorical samples. I know it's like a lot, but really, if you're not following at this point, don't worry at all. So given these expressions, how do we translate it into code? So first, so we have some hyperparameter values set here. Now let me see how to create the vector of mu's. So mu is going to be a vector of values 1 to k. So I have container of, and each of them is individually normal, and normal with mean 0, and it has the inverse variance 1 by sigma squared, and it is so for each of these k mu's. Okay. Similarly, tau is going to be a vector of gamma variables following this alpha and beta, and it is so for all the k values of the inverse variance. Okay. Now phi and z. So phi is a Dirichlet variable, and so the hyperparameter is simply theta. You just pass this in. And z is going to be a container of categorical variables. So there are m of them. So for each such one, so this is going to be drawn from the current sample of phi value. So here, this can be a simple scalar that you have said before, or this can also be a variable. So this is an important point to notice here. And finally, x, you are going to use the z values that you have drawn to index into the mu and tau values. So here, x is going to be a container of a vector of normally distributed variables, where the mu is going to be mu of the current value of zi. This is how I index into it, as we saw before. And similarly, the inverse variance is going to be obtained by indexing into tau using this zi value that you currently have. And it is so for all the m values of x. So I hope it's clear how you translate this model that you have into code. So once you have these individual variables defined, you can again create a model from them. And once you have a model, you can also draw samples. So these are the current values of the samples that I have. And here's another sample histogram plot for all the x values. So there were m x values, and there were like 100 of them. So this is the distribution of all these x values. So this is all you will be needing for the homework. Here's some useful documentation. Feel free to go through them. But note that both of these tutorials use a more complex version, which might not be necessary. But yeah, feel free to go through them as well. Thank you. This is the end of the recitation.